Okay. Where were we before? Uh, yeah, we had the DLL thing. When we created DLL for CUDA, what it did is that in order to have the DLL work, we have to do all of these steps right here: add properties, under properties, and having to do that for every single project just is just impossible. There's no way I'm going to do that. So instead, uh, we're going to learn to load a library manually. Okay, how do we do this? In order to do this, you have to use function pointers. A function pointer is, yeah, I've been reading up on this right here, cprogramming.com. That's where you find it. It just you define a pointer, and then you define a function pointer thing, and you assign it, and then you have a function pointer. And let me just show an example here. Well, we don't need an example. Okay, let's get back to the CUDA. What was I doing? Okay, confusing myself here. Okay. Now we're inside the CUDA library. CUDA library.h. We're gonna take all of these functions right here and then turn them into function pointers. Okay, copy and paste them here. Okay, delete everything. Oh, and one more thing. The reason why, no, right here. The reason why I put if and def C++ right here is because C has a bad habit of decorating the name. So if you call something CUDA neural create, it will instead call it CUDA neural create slash something else, something, and it's completely random. You have no idea what it is. So by specifying if and def C++ extern C, that just tells it to keep the name exactly what it says. It says how it says here. So if you don't put the C plus extern C part here, then the name's gonna be something completely different, and it's just gonna break everything. Okay, let's get back to where we were. Okay, we're gonna turn all of these function names into function pointers. Okay, wait. It's you need to add a parentheses and asterisk. And reverse destroy. Okay, now we have our function pointers for a library. Okay, now you need to call load library. Okay, that's in C. That's in Windows. Windows has a function called load library. Let me find it. Load library. This is to load the DLL. It loads the DLL into memory manually. This way we don't have to add all the other stuff. Okay, handle. What is it? H module. Load DLL. Load library. Okay, H module load library. Now we need to find the library name. The library is just the DLL file. When you compile, it gives you the address of the file. And then we add this here. And this is the next problem. The file names use / and then the C file names use backward slash. I have no idea why it does that, but every time you copy a file name, you have to do that. Change from backward slash to forward slash. Okay, this is the name of the library. Load file name. Okay, we have to set L. Okay. Load library lpcs data lib file name. Okay, why doesn't it like it? Okay, const char wc file name. Oh, why doesn't it like it? Whatever. Load library module handle equals. Okay, now we're good. Equals handle if handle. Okay. Okay, now we have to copy all this. Now just take them one by one, because something's going to go wrong here. Load library get proc address. Okay, I've done this before. I think I know what it means. Get proc address. Oh, okay. Get proc address H module procedure name. Okay, get proc address H module handle and procedure name, and neural array create and text. Nope. Okay, this is the name of the procedure that we're going to be using. Why does it accept that, but it doesn't accept the other one? Okay, now we have a problem again, because we have to set it to the type of the function name, but unfortunately we don't have a type. We could do it when we have a type, but we have to create two different set of names, and that just doesn't make any sense. It would just make everything way too long. So instead is a trick. Okay, void set function, set pointer void pointer function. No, pointer a pointer to a pointer. Void pointer to the pointer function. Void pointer source. Otherwise, C will complain that if you try to compile this, it will fail, because you can't cast a procedure address, a void pointer to a function pointer, unless you know what kind of function it is, because you can cast, each function is going to be different. So unless we want to do some really bad stuff, it really doesn't make sense to do it that way. Okay, all we need to do is star function equals source, and that's it. We're done. Okay, so because set function and get proc address, and we have it. I think we have it. Oh no, we have and function. Oh, we have to call the pointer to a function. That doesn't work. Void, and we have to specify that it's double void, otherwise it will complain. Okay, what are we missing? Okay, right here. No, is it? Yep, that's it. Okay, now we have a function to CUDA neural recreate. So let's just copy it, and CUDA set data, copy, and CUDA is, we have copied that down here too. Okay, CUDA array get data, CUDA array copy, CUDA array reverse. Oh wait, and CUDA neural array destroy. And that's it. All our functions are loaded. So instead of having to go through all these steps to move the file to the add the file to all the other stuff, we just call load library, and it sets the function pointers. Normally we'd have to know what the location of the DLL is, but here we don't. We just pass the location of this DLL right here. This just save time when we're compiling. If we're making a release program, we'd have to do it a different way, because it really doesn't make sense to do it that way. But for here, this is the right way to do it. Testing it here wouldn't make sense because it's already loaded. So I'm gonna have to create a new project and to erase all the stuff that I've changed. Okay, let's just run it. See, build it, and wait. Oh, I forgot something. It's redefined because I'm including it in here, so I have to remove this right here. But I still need all the definitions. I have to copy the definitions. Okay, CUDA neural array. I just copied the definition directly from the other thing, and it works. I have to remove this, otherwise it sees the definition twice. So rebuild. And yep, it works. Now for the next step. Okay, one thing I've always wanted to do is to have a, instead of a type neural array having to, I need a CPU version of the neural network and a GPU version. Just in case the GPU is not available, I can just use the CPU version or the CPU version. So I'm going to go into type neural array, and just copy everything here into GPU into CUDA versions. That's gonna take a little work, but I think you can do it. Okay, what do I need to do? Okay, create a new CUDA library. What was I? CUDA library. Okay, file, new project. Okay, why do I need a CUDA library anyway? I don't remember why I didn't that. Actually, I don't. I just have to copy everything here. Oh, I just copy it. I don't need a CUDA library. Okay, where are we? I keep getting lost. Okay, can I make everything here work? It may be problematic. Okay, I just realized that creating a separate CUDA library just doesn't really make sense, because then the type library and CUDA library will be connected together, and I don't want that kind of integration. So instead, let's do something else here. Let's just turn everything here into function pointers and then load the functions as needed. Just turn everything into a function pointer, because I don't want to retype everything each time. Okay. Type library, just turn everything into a function pointer, and make sure that the CUDA library and the type library are identical. Whoa. Actually, that could be problematic. No, it won't be. Okay. Okay, let's just do this. Okay. So how am I going? By the way, this is what's called a virtual function. The whole point here is to have complete flexibility. I want to have two separate sets of function, one for CPU, one for GPU, and that means I need to be able to switch back and forth between them without changing anything. Okay. CUDA neural array create. Declaration is incompatible. Oh, okay. Oh, darn. That's a problem. Okay, do I set up? Does that work? Yeah. Okay, I'm going to set you have to set it in something different, otherwise the system gets confused. Okay, every name has to be set to something different, and then I need the library. Okay. Okay. This is just tedious. Let me just pause and do it offline, because it's just going to be tedious. Okay, now I'm done. All I did was set everything to a function, set all the functions to function pointers right here, and then change the names of each function in the type neural array to something different, like by adding an underscore at the beginning of every file name. This is to make sure that they're different. And then at the end right here, I added a function to just set all of the function pointer names to actual functions. And that seems like a pointless thing to do, but it's just to avoid having to go through the process of loading the library. It will be just easier just to, well, if it wasn't for having to change the parameters inside Visual Studio. This is just a really ugly solution to a really stupid problem, but it gets the job done. The next thing is that, oh, let me just test it. You have to call the init neural library, this function right here, init neural library each time to set the function to basic values. But we still don't have the CUDA library, so well, I just see if it works. Well, it works. So everything works, but now we need to actually copy all the function to CUDA, and that can get rather difficult. But let's do it anyway. Okay, step 1. Make sure that the type neural array and CUDA neural array are identical. So I'm gonna need type shape right here. Fortunately, we have a type library. Just copy it into CUDA and CUDA library. Wait, CUDA memory. What? CUDA library.h. Include type shape. Do I have to include type shape? Maybe I don't. No, just no. Let's not include. Just copy it. Just make sure everything is the same. Instead of calling include, I'm just gonna make a CUDA library as isolated as possible. Just make sure that everything is identical. But we're not going to attempt to make everything to have anything in common. Just copy everything and get it over with. CUDA shape. Although that might not make sense itself. I'm not even sure what I'm doing. Would include be better, or would having type shape be better? Oh, shoot. Oh, it just doesn't make any sense, really. Okay, I'm just going to include type library. Since we're just going to compile them side by side anyway. Type shape. And from there, just make sure everything is identical. CUDA neural array, type shape. Okay. It's very important that everything be as close to the same as possible. Okay, type def double. Should I do include here? But I don't like doing that. I'm gonna make one exception here, but otherwise we're just confusing ourselves. I just don't like the idea of having the DLL be a separate thing, but that's one thing that has to be that is very necessary. Okay, CUDA neural array. Let's start with the functions. Create. Let us copy it exactly, or almost exactly. Kernel.cu. CUDA neural array create. Okay, type shape assign. Oh, so it has to be different. Type shape assign. Oh, wait, height length. Okay, CUDA shape assign. Just try to copy everything as close to the same as possible. What do I need to copy? If CUDA memory allocate. If CUDA memory allocate data. Actually, we don't have to copy much. CUDA null array create. Just copy the name. CUDA null array. CUDA null array type unit. CUDA null unit. And that's about it. Okay, we don't need this right here. Okay. It's just gonna take forever to get this to work anywhere near the same, but type null array, set data. Okay, this is gonna be really tedious. I don't think I want to have to do this. Okay, type null array copy. Oh, where are we? What is this? Oh, that's a completely different copy of it. Oh, this is wrong. Okay, type null array. Open it here. Okay, there it is. That's better. Okay, type CUDA null array copy. Let us set data. Okay, type null array. Oh, I'm just gonna set everything to the same thing. Let's go offline and just start copying it, because otherwise it's just gonna be tedious. Okay, so far all I did was copy the first three functions: set data, get data, array copy, from the CUDA library into the type library, into the type functions. There's really no difference. You just change a CUDA memcopy to just standard memcopy. But here we have something that really takes some work. It's like there's no big difference really, but except for one little problem. You cannot copy in from CUDA memory directly, meaning you cannot manipulate the memory. Well, you have to do all this setup right here, and you can't do that directly with CUDA memory. So you have to allocate a buffer before you can do anything. Okay, CUDA. Change everything to CUDA and CUDA. Okay, we're almost done. CUDA null unit buffer. CUDA null unit. And just set everything CUDA null unit, CUDA null unit, CUDA null unit. Okay, the buffer. Buffer is just parent.array data. This simply does not work at all. So instead, we're gonna have to allocate the buffer. Buffer equal malloc, allocate memory in the standard memory. Malloc parent dot array size. Okay, CUDA null unit parent dot array size. Okay, now we have the buffer. We're setting the image RGB. malloc is on the shoot. So show potential fixes. Okay, malloc. We have to include stdlib. That's just a tedious thing. Okay, now we allocate the buffer. Next step. Now that we have allocated the buffer, we have to, of course, we have to check if buffer is right. Okay, if buffer equals 0, return 0. Okay, now we set everything. Okay, we set everything as normal, but now we have to call null array set data. Fortunately, it's quite simple to do. CUDA null array parent, CUDA null array unit buffer, and parent.array size. Parent.array size, it's already been allocated, so it really doesn't matter. Okay, parent.array size is allocated perfectly, so oh wait, no, not it doesn't work. It doesn't work. Buffer equal parent.array length. No, parent.array length, not parent this size, length. Oh, that could have been problematic. Okay, parent.array length. The length is correct. Okay, this is because we cannot write directly into CUDA memory, so we have to allocate the we have to first allocate the memory and then copy into CUDA memory. Now we have to free the buffer. Free buffer. Okay. Now it's good. Now we have to do the same for the other one. Get image RGB. Oh, we also need max out. We have to copy everything here into the other one. Fortunately, shouldn't. The reason we're doing all of this because it's going to get complicated later because we have to learn how to do kernels for every single function because it's really not obvious at all. Okay, CUDA neural array. CUDA neural. Just copy and paste everything. CUDA neural. CUDA neural. Oh, no. CUDA. Whoa. Oh, that's bad. CUDA neural. Am I missing anything? Yep. CUDA neural unit parent. CUDA neural. Okay. Now, neural max out. It doesn't matter. Okay, buffer m equal malloc. Parent.array size. Array size. This is why I always specify the size of each array. Otherwise, we have to recalculate every time. If buffer equals 0, return 0. Okay, now we have to do the same thing we did here, but instead we have to get the data, and we have to do it before we get anything. Okay, we have to do it up here, otherwise it won't work right. Go down and get data parent.array length. Okay, is it get data? Oh, wait, I'm confusing myself here. Free buffer. Free buffer. Is that right? I think it's right. Okay, let's just make sure I didn't make any mistakes here. Okay, free buffer, return 1. Yep, color equal data. Yeah, it's right. Okay, now we're going to continue and copy things one by one. I completely forgot I already had a copy function. Do we use memcopy or the one that copies one by one? Which one is faster? Just to be clear, I'm going to use that one instead. Because it does more checks. If parent.array length equals source.array length, I have to decide which one I want to keep. Get rid of that one. Okay, no array field 0. Okay, now our first test. We need to learn how to fill 0, how to use globals. Okay, we already have reverse right here, so we're going to use that one. Okay, kernel fill 0. Kernel fill 0. Oh, we don't need source. Oh, there's no source, it's just result. Okay, no result. We need length, we need everything the same length equal 0. Okay, here's the basic idea of CUDA kernel functions. Every time you see a for loop, you just replace it with a kernel call right here. There's going to be a lot of those. Just every time you see a for loop, just replace it with a kernel function, and that's the basic idea. And of course, you have to call device synchronize. Okay, let's see CUDA neural array parent. If parent equals 0, return 0. Okay, we just copy and paste. Okay, again, basic idea. Just take the for loop and replace it with a kernel call. That means you're calling a thread for each one. Okay, kernel fill 0. and no source, and result. Result dot array length. Kernel fields it, and then of course you call synchronize. Okay, that's the first one. Just replace the for loop with a kernel call. Okay, no, CUDA. No. CUDA neural array field 0. Okay, am I missing anything? Nope. Everything's good. Okay, we have to do it for each one by one. Well, where am I? Kernel field ones. It's basically the same thing. We don't need to copy and paste. Just kernel field 0 and just copy this. Kernel field ones. Change the names. Ones. And of course set this to 1. And set this to 1. And we got one down. Next. Random. Oh. Okay, this one's gonna be tedious. Instead of using our own random functions, I'm just gonna use the built-in CUDA function. And also there's a problem. The random function that we normally use doesn't work inside CUDA. CUDA has a very limited set of functions that it uses. So we can't just call normal functions inside a CUDA kernel. So let me do this one step at a time here. Okay, now we need to figure out how to do the normal CUDA functions. I'm going to look up in the documentations and just wait. Okay, we're back. I got the documentation and it says to use CUREN kernel and CUREN other stuff here. Okay, well, I need to copy this. CUDA neural array parent. Okay, do I have everything? Oh, I forgot to remove the I values. We don't need those. Okay, that's something I forgot to include here. No, we don't need that. Okay, we don't need those. Field 1s, field 0. Oh, and one more thing. It can be really difficult to see where the kernel begins because these two functions right here come as a group. So as a thing, let's just add a line just to make it easier to see where where a function and another one begins. Okay, let's just copy this. We're just gonna put this before each kernel just to make it visually easy to spot where each function begins. Okay, CUREN field random array. Okay, kernel field random. Let's get a kernel. Okay, kernel field random result length. Okay, now we need a CUREN init. CUREN. CUREN is the CUDA random init. That's the CUDA function for initializing the CUDA random, and we need a seed. Where are we gonna get a seed? Oh, each kernel has a separate seed. Oh, yeah, just unsigned long seed. Yeah, sign long seed. Okay, unsigned long seed. Not seed. No, what am I doing? Seed 0. Okay, direction vector 0. And the parameters is state. Okay, CUREN state. Okay, I need this here. So I put it up here. No, CUREN state. CUREN state. Oh, and one more thing. This particular kernel right here, it instead of calling several kernels to do random. We only need one, because otherwise we're gonna have to create different states and then call all the random values with the same seed are just going to give you the same value. So instead we call the seed just once, because otherwise you're gonna fill the entire array with the same value multiplied many times depending on the seed, and that just wouldn't be good. CUN inet, okay, for I. Now we need to call for I equals 0, I less than length. Okay, by the way, the 1 and 1 here, that just tells us the kernel to just call one single kernel. Fill random, not one, random. He only creates one single thread instead of multiple threads. All less than length. I plus plus. Okay, now what? Okay, result equals. Okay, what random do I use? CU rand uniform. CU rand uniform. Okay, CU rand uniform, and we need end state. Okay. Whoa. Oh, CU and init. What is that? No, result.I. What am I doing? I equals, get rid of that. We format this part. Okay, now we have a random number generator. Oh, I'm not gonna do all of them tonight because otherwise it's just gonna take way too long. Let us continue to do everything later. Okay, I'm just getting in the basics down. CUN random, CUN state, field random. I'm just keep the names the same. Kernel reverse. Let's do one more, and then. Oh no, we don't need to do one more. Add is the same as subtract. Let's just do a hard one. Star. Oh wait, that's just way too hard. Okay, let's do these basic, because they're basically the same thing. So we're just gonna copy them. Okay, CU rand CUDA neural array field random. CUDA neural. CUDA neural array add. Let's copy this and this also. Let's copy this right here. Oh wait, we already have this one. Just use that one. This one's easier. Kernel add. Then result source, no, value 1. Value 1 and value 2. Okay, no, value 1 dot I plus value 2 dot I. Okay, add null array add, and just copy all this. Blocks per grid, grids per block, kernel CUDA null array synchronize. Do I have everything here? Oh, I forgot synchronize. I forgot synchronize up here. This is not optional. You have to have this. Let's copy this right here. Wait a minute, do I have this? No, we have. We need this down here. Kernel add. Just replace all the for loops with threads. Parent.array length. Oh, parent.array length plus per block. Source value 1. Value 1. And value 2. So far so good. Parent. Just make sure I didn't miss anything. Value 1, value 2, array, value 1, value 2, everything's good. Add is just plus. No, we don't need that. Okay, for unsigned line, IJK. Okay, add, subtract, add, subtract. Let me just copy it, subtract. Am I here? Oh, yeah. Subtract is minus. Subtract here, and kernel subtract. So no add. Just make sure you get it right. And hopefully you didn't miss anything. Okay, multiply. Okay, so that's really the lesson here. Just convert all the for loops into kernel calls, and that should get you everything you need. For loops into kernel calls, and then we're done. And then now divide. Divide. Oh, we're just gonna copy everything exactly the same. Whoa, oh no, divide. Okay, where is it? Ah, there we are. Okay, divide is if value 2 dot. We just keep everything result. Value 1 dot I, value 2 dot I, result I equals 0. Copy, divide. Oh, I'm still in multiply. Oh, I completely forgot to copy multiply. Okay, so far so good. We have the basics down, the basic arithmetic functions. Next time, we're going to get into the really complicated parts. Index map copy and all the index map functions. These are going to be very, very tedious. Okay, just make sure we get everything right here. One more cosmetic stuff. Kernel array fill, no, CUDA neural array fill random. Yeah, kernel fill kernel add. Now come on. Kernel subtract. Kernel multiply. And kernel divide. Hopefully you didn't miss anything. If we miss something, I'm gonna fix it later. So we don't have time for this right now. So that's just the first part. Replace all the for loops in the CUDA neural array with kernel calls, and that's the basic. Except it's gonna get a lot harder once we get to these kind of for loops. That's just not the same at all. Okay, well, okay, that's good for the night.